So this session, Cosmology and Faith, it's a privilege to welcome again Rodney Holder, who's well known to many of you, I hope. He was the course director at the Faraday Institute from its inception in 2006, so we're just celebrating our 10th anniversary. Rodney has a background in mathematics and physics, with a DPhil in physics, and that subsequently, after practicing in industry for a while, was ordained and has theology qualifications as well. So Rodney is well experienced to be able to come and talk to us on cosmology and faith.
Thank you very much. Is the sound okay for everyone in here? Good. Well, I'm going to talk about the Big Bang, and you may recognise the person here on the right of this picture. I hope pretty much everyone, whether they've done science or not, recognises Albert Einstein. The person on the left is much less well known, but he is the father of the Big Bang theory. This is Georges Lemaitre. He was actually a member of this college from 1923 to 24 when he was researching with Arthur Eddington at the University Observatory. And he, as you can see, is a priest. He was a Catholic priest, as well as one of the greatest cosmologists of all time. So what he did was to solve Einstein's equations of general relativity, that's Einstein's theory of gravity, for the universe as a whole. And he came up with a solution in 1927 which showed that the universe was expanding. The expansion was observed a couple of years later by Edwin Hubble. And then again in 1931, Lemaitre found another solution of Einstein's equations in which not only was the universe expanding, but it was expanding from essentially a point, a highly compact initial dense state, which Lemaitre called the primeval atom, which was later dubbed the Big Bang by a chap called Fred Hoyle, working here in Cambridge, who very much disliked the idea, in fact proposed an alternative to explain the expansion. That was the steady state theory. According to the steady state theory, you can explain the expansion by having new matter come into the spaces between the galaxies, basically the fundamental units of the universe of galaxies. They are being pushed apart as space expands. But Hoyle explained how that could arise if new matter came into existence at just the right rate between the galaxies, and new galaxies formed and so on. Well, what happened was that the Big Bang triumphed in the end. It's extremely well supported by evidence now, and the steady state theory is not compatible with the evidence. So there are a number of strands of this evidence. The main one came in 1965 with the discovery of the so-called cosmic background radiation. This had been predicted back in 1948 on the basis of the Big Bang, by a group of cosmologists in the US. Suppose the universe started from this hot, dense state. Well, it would have been hot and at the beginning, and as it expanded, it would have cooled down, and it would have left this remnant radiation bathing the universe. The prediction was about 5 degrees above absolute zero. It turns out to be 3 degrees above absolute zero, which is very close to the prediction. Absolute zero is minus 273 Celsius, so it's pretty cool over there. The discovery of the background radiation was made by these two chaps, Penzias and Wilson, at Bell Telephone Labs in the US. They thought they'd got bird droppings in their antenna. What they'd got, in fact, was the remnant radiation from the origin of the universe, the Big Bang. They got the Nobel Prize for this discovery. But of course, what they discovered had to be explained to them by cosmologists who understood what was going on. Now, just to give you a flavour of what we're talking about in cosmology today, this is a typical galaxy, as it's very much like it, though you can't see a galaxy in this kind of way. So this spiral galaxy contains something like 100 billion stars. If it were our galaxy, the sun would be a very ordinary star somewhere out on the edge of a spiral arm. And there are something like 100 billion galaxies in the observable universe. That gives you some idea of the scale. This may not look much to you, but I think it is a really fantastic picture taken by the Hubble Space Telescope. And in this picture, each of these little blobs is a galaxy, and this is the Hubble Ultra Deep Field. These are the earliest galaxies to form in the universe. We're looking at the universe as it was when it was 5% of its present age, something like 13 billion years ago. Because light takes that length of time to reach us, 13 billion years. So the current estimate of the age of the universe is about 13.8 billion years. Now, the story is that as the original matter density of the universe expands, out of this sort of almost uniform nature of this matter energy, you get instabilities which form galaxies, and within the galaxies you form stars. And within the stars, all the chemical elements, the stuff of which you and I and our planet are made, are built up from just the hydrogen, a bit of helium, that's 25% helium that's bequeathed us by the Big Bang, and all the carbon, nitrogen, oxygen, and so on is built up inside stars. And then at the end of their lives, when they run out of the nuclear fuel that's keeping them going, these some of the most massive stars at any rate explode and spew out all the material they've created into the surrounding medium, and you have the material ready for the next generations of stars, which then can have planets, and ultimately there's the possibility of life, because all the material has been manufactured for life. And this is a famous example, again taken with the Hubble Space Telescope. This is the Crab Nebula. You've had a star explode and spew out all this material into the surrounding medium. This was first observed as a new star by Chinese astronomers in the year 1054 AD. This is another example, looks rather different, but essentially you've had a star in the middle which has blown off all its material into the surrounding medium, and it's lit up the material in this. There's a giant shockwave gone out from the centre, and it's lit up this material in this kind of necklace pattern. So that's an absolute whistle-stop tour of what the Big Bang theory, the current theory for the origin and evolution of the universe, is about. And it seems to me that it raises two, or at least potentially raises two interesting questions that relate or may not relate to theology. And these are, well, it looks like the universe began to exist 13.8 billion years ago. And the second is that it looks as though the universe is very fine-tuned, is in the jargon for life. Seems to be set up in a very special way in order for all these processes that I just described, manufactured elements and so on, to happen so that life arises within it at some stage of its history. And I'm going to talk about those two issues. So what do we make of the beginning to start with? Well, St. Augustine has been mentioned already. Here's an interesting picture, a painting of him I saw a few years ago in Florence. It's by Botticelli, and he's painted, there are scientific instruments around the place. Anyway, in addition to that wonderful remark that Andrew Davison quoted to us about not looking fools for saying silly things about what we now call science, he said this about creation: assuredly the world was made not in time, but simultaneously with time. Augustine saw from his Christian theology that space, time, and matter are all created. So time comes into existence with the creation. And this is a very interesting idea. And indeed it chimes very neatly with the Big Bang, if you think about it coming along 1,500 years or so afterwards, that time and space and matter come into existence 13.8 billion years ago at the Big Bang. Of course, Augustine could know nothing about the Big Bang itself at that time, but this is what his doctrine of creation led him to say. Now, the idea that the universe had a beginning is extremely troubling to some atheists. It was very troubling to Fred Hoyle, whom I've already mentioned, who proposed the steady state theory. He was an atheist. It's very troubling to Stephen Hawking today. And Hawking has proposed an alternative for what happens near what we might have called the beginning. He called his no boundary proposal. And according to this proposal, what happens as you track the history of the universe back nearer and nearer, what we would call t equals naught, in fact something strange happens. Time becomes imaginary, according to Hawking. Now, that term imaginary has a very technical meaning in mathematics that anyone who's sort of maybe done maths A-level would understand, to do with imaginary numbers and so on. But for him, what that seems to mean is that the universe doesn't actually have a beginning. And he says this: so long as the universe had a beginning, we could suppose that it had a creator. But if the universe is really completely self-contained, having no boundary or edge, it would have neither beginning nor end. It would simply be what place then for a creator. That was back in Brief History of Time, his first book, and then his more recent book, The Grand Design. He says, again, the same thing, and there would be no need for God to light the blue touch paper at the beginning and set the universe going, which is the only role that Hawking sees, in any case, for God. Now, there are actually very serious scientific and philosophical problems with Hawking's proposal, and not least is this idea of imaginary time. What that means in practice is that time becomes like another space dimension. So instead of 3 dimensions of space and 1 of time, you end up with 4 dimensions of space near the beginning. Now that's philosophically problematic, because time, real time as we understand it, measures change of state from one state to another. So if there's no time but there's only space, how do you get from that initial state, which might be eternal, but how do you get from it to another state? And anyway, there are quite serious philosophical problems about that as well. And there's another problem that is raised by a colleague of Hawking's called Alexander Vilenkin. Now, at the beginning of 2012, there was a symposium in Cambridge to celebrate Hawking's 70th birthday. It's utterly remarkable that Hawking has reached now 74, given his terrible physical condition. And I first came across Hawking when he'd only just developed the disease when he was about early 20s. And he's carried on and done remarkable work. But anyway, at this symposium, sadly, Hawking himself couldn't be there because he was ill. He had one of his periodic stays in hospital. He sent a message to the symposium saying, well, if the universe had a beginning, then it would need God to create it, and so on, all the same stuff. But this man, Alexander Vilenkin, and colleagues have proved what are known as singularity theorems, which track back the history of the universe to the earliest possible times. And these singularity theorems show that the universe are all the basic modifications of the Big Bang that are on offer at the moment, including multiverse models that I'll go on and talk about in a minute. The universe does track back to a beginning. And he said at this symposium for Hawking's 70th birthday, all the evidence we have says that the universe had a beginning. Now, it seems to me that suppose it didn't have a beginning. Well, the fact it certainly looks like it had a beginning is a problem for atheists, but it didn't have a beginning. That wouldn't be much of a problem for theologians. St. Thomas Aquinas, going back to the 13th century, again, who has been mentioned, said this: "By faith alone do we hold, and by no demonstration can it be proved that the world did not always exist." He believed it did. It did have a beginning from his understanding of Scripture, but he thought you couldn't actually demonstrate that. Nevertheless, even if it didn't have a beginning, it would need God to create it, according to Aquinas, and this is what his 5 ways, his 5 proofs of the existence of God are about. And I'll come back to this point in a moment. But meantime, let me just go to another idea that's out there in cosmology called quantum vacuum creation. My goodness. Sounds terribly technical, and indeed it is, but here's a chap called Lawrence Krauss who has written a book called A Universe from Nothing. And he thinks, indeed Hawking says the same thing too in different places, that the universe creates itself out of nothing. Now, for Krauss and Hawking and others, this nothing isn't really a nothing. It's something called the quantum vacuum. Now, in quantum theory, the theory of the very small, the vacuum is not really empty space. It's certainly not nothing, because what happens in the vacuum in quantum theory is that particles come into existence and go out of existence before I could snap my fingers in a small fraction of a second. They come into existence and annihilate and so on. The idea is that you could get some runaway effect whereby the universe comes into existence as a result of these sorts of processes. So the quantum vacuum is certainly not nothing. It's a very sophisticated something, and according to Krauss and so on, it even has it has lots of properties, including, well, nothing is unstable. Well, this is not the kind of nothing that would trouble philosophers or theologians. Here is an analogy for what's going on here, it seems to me. So here's Alice in The Looking Glass and the King, and there is this very interesting conversation. "I see nobody on the road," said Alice. "Well, I only wish I had such eyes," the King remarked in a fretful tone, "to be able to see nobody, and at that distance too." "Who did you pass on the road?" the King went on, holding out his hand to the messenger. "Nobody," said the messenger. "Quite right," said the King. "This young lady saw him too." "So, of course, nobody walks slower than you." "I do my best," the messenger said in a sullen tone. "I'm sure nobody walks much faster than I do." "He can't do that," said the King, "or else he'd have been here first." So in this you see the real confusion between nobody in the sense of the absence of any person at all, and a nobody with a capital, and a Mr. Nobody. And it seems to me that this is the confusion that's going on with people like Krauss and Hawking, saying that the universe creates itself out of nothing, and redefining nothing to be a very sophisticated something, the quantum vacuum. But what I really want to move on to talk about is the idea of ultimate explanations, why there is something rather than nothing. And it seems to me, as Andrew Davison was saying, that this is what the Christian doctrine of creation really addresses. Now, the question is then, why is there something at all? Why is there a universe at all? And it seems to me that only God can provide an explanation for this. And no scientific theory can actually do that. And I'm going to introduce a couple of terms from philosophy to expand that. Well, in theology, God is a necessary being. To say that God is necessary means that God cannot but exist. God exists in all possible worlds. There never was when God was not. God is, if you like, eternal. Now, In contrast to that, now, that's really part of, at least part of what we mean by the very term God. And in contrast to that, the universe is contingent. Well, there may or may not have been a universe. The universe could be different from what it is. God's attributes inhere in God necessarily. The universe is contingent in that it might have been different, it couldn't have existed in the first place. So the idea of God as necessary being explains why there is anything at all that's contingent. It's his creation. And so when someone like Richard Dawkins then comes along and says, yeah, but who created God then? That's to misunderstand the meaning of the term God, because anything that's created or comes into existence is certainly not God. You can argue about whether a necessary being exists or not, but if God as necessary being exists, then that God explains why everything else exists. And it's rather interesting that this point has been recognised by some of the physicists around, including none other than Stephen Hawking, when he wrote back about the history of time, because back in that book he said, what is it that breathes fire into the equations and makes a universe for them to describe? Indeed, you can have the most wonderful theory of physics. Hawking is looking for a theory of everything. I'll talk about that in a minute. But why is there a universe to which that theory applies? And then here's Martin Rees, until recently President of the Royal Society and Master of Trinity and still Astronomer Royal. Colleague of Hawking's, he said the same thing. Such questions, why there is something rather than nothing, lie beyond science. They are the province of philosophers and theologians. This man was a very great cosmologist called Dennis Sharma. He supervised the doctoral theses of Hawking and of Rees, and indeed at a much humbler level, I have to say, of Rodney Holder. And he made the same point though. He said none of us can understand why there is a universe at all, why anything should exist. That's the ultimate question. Well, certainly science can't do that. And it's interesting that each of Hawking, Rees and Sharma recognise this point, all three of them atheists. But they recognise that, well, science can't explain why there's a universe. You have to go to philosophy and theology. Okay, so that's really the first part of my talk, and the second part is about this so-called fine-tuning, the specialness of the Big Bang, the special way in which it seems to have been set up. And that relates to two kinds of quantities, if you like. The initial conditions back at the Big Bang, 13.8 billion years ago, and the physical constants, the constants that go into the laws of physics, which describe the forces of nature, the relative strengths of various fundamental forces of nature, like gravity, like the forces which hold atoms together, and so on, and the masses of the fundamental particles, the proton, electron, and so on. And I'm just going to give a couple of examples to give you the idea of this, the flavour of what's being said here. Now, if you go back to 1 second from the origin at the Big Bang, the mean density of matter energy needs to be what it was, the 1 part in 10 to the power 15, in order for galaxies and stars and ultimately life to form in the universe. The universe is sitting on a knife edge between expanding forever and ultimately recontracting. And it needs to be on this knife edge, in order for life to arise. If the mean density of stuff were more than this certain critical value by this tiny amount at 1 second after the Big Bang, if it were more, then the universe would recollapse far too quickly for anything interesting to happen. Gravity would pull it back, and nothing interesting would develop. Too short a lifetime, months, years, hardly any time to do anything. Then, if, on the other hand, the mean density were lower than this critical value, the universe would expand far too quickly for gravity to form condensations and galaxies and stars and so on. So nothing interesting would happen. Now the second example, I think, is possibly more interesting, and this relates to the strong nuclear force which holds nuclei of atoms together. And that needs to be just what it is, to a high degree of accuracy, in order for carbon and oxygen, the building blocks of life, to be made inside stars. Now, to make carbon, what you have to do is to crash 3 helium nuclei together and make them stick. And to do that needs a very special effect within the carbon atom, which is related to the strong nuclear force. Because if you just crash 2 of these nuclei together, you get the element beryllium, but it only lasts for a fleeting tiny fraction of a second. So you've got just that tiny fraction of a second to crash the third one on. It needs an enhanced effect. And then what you don't need is to, when you make oxygen, by crashing a 4th helium nucleus on to carbon, to destroy all the carbon in the process. It's a very, very fine balance of what's going on here. And the interesting thing is that the person who discovered that was none other than our atheist cosmologist friend, Sir Fred Hoyle. He was moved to remark when he made this discovery that a super intellect has much to do with physics as well as with chemistry and biology, and there are no blind forces worth speaking about in nature. This is a man who broadcast on the BBC and gave lectures in which he said that religion is an illusion. But he's moved by his science to talk about a super intellect behind physics. So, there are lots more examples of this sort of thing. I'll come back to 1 or 2 more in a moment. But of course, this is an idea. Sometimes goes under the name of anthropic principle. All this stuff I'm talking about, which relates to the conditions needed for anthropoi, human beings, to come into existence, but really any life. And it's a puzzle for cosmologists. This is Paul Davies, very well-known cosmologist. I've had the privilege of debating with him a couple of times. He says this, like the porridge in the tale of Goldilocks and the 3 Bears, the universe seems to be just right for life in so many intriguing ways. Now, what might be the explanations for this? Well, there is a very natural explanation. If you think that the universe was designed by God, then a God who has purposes and intentions for the universe that will bring about life, that will bring about intelligent creatures able to have a relationship with him and so on. That seems to be a coherent kind of explanation. So what about if you're an atheist? What alternatives are on offer to you? And there seem to be 2 main ideas out there. The first is that I'm actually wrong to say that the constants of physics and so on could be different, or that if you change the initial conditions, things would turn out different. The universe somehow has to be the way it is, and there is no alternative. If we find this ultimate theory of everything that Hawking and others are looking for, maybe it will calculate all these numbers from a more ultimate theory. Einstein at one point said, what I'm really interested in is whether God could have made the world in a different way. So it doesn't, of course, preclude God as the creator of this idea, but it does constrain what kind of world God could make. Then the other idea is the direct opposite of that. Is to say, well, yes, all these constants can vary, they do vary. In other universes, so a multiverse is a gigantic collection of alternative other universes, many universes, and usually infinite number of universes in which everything that can happen does happen somewhere, sometime, in some universe. All the constants get juggled around. We shouldn't be surprised in this universe because, well, we couldn't be in any of the others, where the constants are a bit different because, well, this is all dead. So we shouldn't be surprised to be in this one. So those are the ideas that are out there, and I think they are pretty problematic, actually, for various reasons. So for atheistic strategy, there are actually two ways of thinking about this. If there's only one set of laws even, then it's a deep puzzle as to why the only set of laws gives rise to. If there's one set of laws in which all the constants are calculated and determined, then it would be deeply puzzling that this set of laws gave rise to a universe with life in, I think, when you can imagine so many different kinds of worlds that are completely dead, just a few particles floating around in empty space or something. How come? And the sort of lesser version of this hypothesis, well, maybe there are lots of different laws, but given that our set of laws for this universe, the constants have to be what they are. Well, then you ask, okay, but why is this the set of laws that applies to the universe? If there are other sets of laws which could apply, but which give rise to dead universes and so on, why does this set of laws apply? So you're left with some puzzles. Now, the much more popular idea is that there's a multiverse, then you still have problems. You have to ask why this multiverse as opposed to another, because there are lots of different ways of getting multiverses. You're getting sets of many universes. So why this multiverse in which at least one member universe has a life in it, as opposed to all the possible multiverses which are dead with no life-bearing universe within them. The only way really to avoid that is to go for the ultimate, extravagant, maximal multiverse, something like the one that's offered by the cosmologist Max Tegmark, in which all possible mathematical structures have physical existence, all possible multiverses exist. Well, then you guarantee that this universe exists, but how can we have any possible evidence for that? Sorry,
with the multiverse, if all possible possibilities could exist, could that mean that one possibility could exist where there is a God?
Yes.
And so it's a self-defeating concept.
Yes, thank you. That's absolutely right. The ontological argument for God's existence works if this is the case, because if God is possible, then there will be a possible universe, one of these existing universes, they're made existing now, will exist in which God exists. And of course, if God is possible, if God exists in one universe, then because God is necessary being, he exists in all of them. It's a proof of the existence of God on the basis of the multiverse. So yeah, if it's a method of avoiding the existence of God, it's self-defeating, you're right. So let me go on to some recent developments in cosmology. Now here's Alan Guth, who has proposed something called the theory of inflation. This applies to the first tiny fraction of a second from the origin. You've got time on this axis and space dimension on this axis, or those two axes, if you like, you can see. And in the first 10 to the minus 32 seconds, 1 divided by 1 with 32 noughts after it, that fraction of a second from the beginning, the universe underwent an incredibly rapid period of expansion, and then it tailed off into the gentle expansion of the sort of standard Big Bang. Now, what this theory does is it drives the mean density to the critical value, and it solves some other problems with the standard Big Bang. And so you solve you solve one of the fine-tunings at any rate. Okay, it drives the universe to a uniform state, in which means that galaxies and stars can form. Now the problem, and this was of course meant to be heading us towards a more ultimate theory, theory of everything. The problem was, though, that inflation itself needed fine-tuning. So constants within it needed to be set to specific values in order for it to work. You need the right period for which inflation happens and so on, before it dies away, and all that sort of thing. You need fine-tuning anyway. So More recently, cosmologists have gone for a multiverse version of inflation, chaotic and internal inflation variance, in which you get a single, oh sorry, you can't see right at the bottom of the screen. Chaotic and internal inflation. These are versions in which you get lots of different, you get an overarching infinite space in which you get inflation happening in some places and other places, and then universes bubbling up out of other universes ad infinitum. So it's a multiverse version of inflation. And a further development is this. This is a man called Leonard Susskind, and he is a pioneer of something called string theory. You don't need to know about the details, but it's getting away from the idea of particles as tiny points, points of matter, but instead they're vibrating strings, and the different ways the strings vibrate are the different particles. Now, when you track back very, very near to t equals 0 at the beginning, you need a theory which combines quantum theory, the theory of the very small, with general relativity, Einstein's theory of gravity. And string theory is a candidate theory for it. And it's meant to be a more fundamental theory than what we've got at the moment, the standard theory of particle physics and so on. And the problem with, after about 40 years or so, it's made no predictions, this theory, which can be tested in the laboratory. No predictions, nothing to verify it, and so on. And Leonard Susskind, who I've again had the privilege of debating with, now says, oh, well, that's actually a strength of the theory. Maybe there are, and he's moved to a multiverse version of string theory called the landscape. He says that there are something like maybe 10 to the power 500 different solutions, one with 500 noughts after its solutions to string theory, all of which exist in different universes. Okay. This is a cosmologist, physicist called Lev Landau, Russian Nobel Prize winner. Anyway, he has this rather interesting thing to say about cosmology. Cosmologists are often in error, but so tight. It's an interesting quote because there's some fantastic observational work done in cosmology at the moment. There's great theoretical work, but a lot of the theory is now outstripping the observations. And we're in the realm of speculative theories that apply to the first 10 to the minus 43 seconds from the Big Bang and so on, like string theory. 1 divided by 1 with 43 noughts after it, seconds from the Big Bang, for which there is no evidence. And it's a problem. And that brings me on to problems with the multiverse idea. I mean, God could create as many universes as he likes, of course, and there are theologians who like the idea of multiverses. I'm on this more skeptical side of this spectrum. So the first point is that the physics is speculative. We can never receive any signal from any of these other universes that are out there, supposedly out there. Not even in principle can we receive a signal, because the space between is expanding at faster than the speed of light, and signals can't travel at faster than the speed of light, so there's that sort of limitation. Then there is a problem about invoking infinitely many universes. Of course, to cover all your bases, you need infinitely many, to cover all the possibilities. And there is a real problem about that. You start to get paradoxes when you talk about infinitely many existing things, existing universes. Mathematicians play happily with different degrees of infinity, but infinities in the physically existing infinities are more of a problem. There's a famous example with the mathematician Hilbert, who ran a hotel which had infinitely many rooms, and the problem was that they were all full. And sort of a new guest turns up at reception, and he scratches his head and he says, well, okay, I can deal with that. I can put the person in room 1 into room 2, the person in room 2 into room 4, the person in room 3 into room 6, and so on and so on. Behold, all the even numbered rooms are full, but all the odd numbered rooms are now empty. Room for infinitely many new guests. In fact, you can never complete an infinity. This is the point. You can never actually cover all bases because you can never complete an infinity. There's a problem about human identity. I mean, as soon as you start to multiply up universes in this extravagant kind of way, you end up with lots. Okay, a very tiny minority, but other universes in which there'll be a lecture room looking a bit like this, with somebody looking at, like me, giving it, but in others of those universes in which the character says, well, actually, I'm retired now, why am I bothering to go along still? And so on, you know, so there'll be different variants, or they'll go off in different ways. It doesn't defeat the idea. But if we can do it without paradoxes, aren't we better off, at least metaphysically better off? And for this sort of reason, I think this isn't a simple hypothesis. And there are, as soon as, again, you start to think about it, you can think about ways in which well, it's not simple because it invokes many entities. William of Ockham, back in the 14th century, said that we should not multiply entities needlessly. We only need as many entities as will explain the data, and that's been a principle for science to operate under. There's a lack of predictability when you enter this realm of infinitely many universes, because we sometimes talk about a God of the gaps, okay, in the science-religion dialogue. We're invoking God, say, to explain why the tail of the bacterium, comes into existence, the thing that wiggles it, intelligent design, capital I. It's a God of the gaps, because science can come up with an explanation for that. Well, there's a possible multiverse of the gaps here, because we can find unusual features in our universe, in the lab, and we could be tempted to say, well, hang on, that odd thing will happen in a multiverse, somewhere in a multiverse. We could be tempted to go for a multiverse explanation rather than, if you like, a normal scientific explanation. And in terms of predictability, there will be many, many ways in which this lecture could go in the next 10 seconds where I don't complete it, or the space-time continuum falls to pieces in some kind of dramatic way. The principle of induction, which we use to do science, falls apart, and so on. There's a problem with something called the cosmological constant. You may remember when I drew that diagram, I ought to reproduce it. This diagram here. The universe, this little upwards curve shows that the universe is the expansion of the universe is accelerating, and that feature was discovered a few years ago, and it's to do with something called the cosmological constant. This is a number that, a constant that Einstein put into his equations originally in order to make the universe static. He didn't like the idea of the Big Bang at all originally. So he wanted a static eternal universe. And he set it to a particular value to give a static universe. Well, it now turns out that, and then it was abandoned, but now it turns out that there is a cosmological constant of a certain value. It's like a repulsive force, an anti-gravity, and that's causing this acceleration. And it takes a tiny value. The problem is the tiny value, because cosmologists think they know what it is. They think it's to do with, going back again to the energy of the vacuum, and they calculate it. And they calculate its value to be something like 10 to the power 120 times the value that it takes in our universe. And that's the value that's compatible with life. If it took anything well, even 100 times the value it takes, galaxies couldn't form. But if it took anything like 10 to the 120 times the value it takes, our bodies would fly apart to opposite sides of the universe before I could click my fingers. So it's a major problem for cosmology, and of course the idea has been to go for a multiverse type of explanation. Oh, well, there are lots of universes with different cosmological values of the cosmological constant. That's probably the area where this multiverse theory comes closest to being successful, actually, and that sort of explanation. Ask me about that if you want. To get a multiverse in the first place, most of the kinds of multiverse that are out there on offer at the moment does require still some fine-tuning, because it needs the mean density of all the stuff in the universe to be less than the critical value of all the stuff in the overarching space-time. When we talk about different universes, we're not really talking about different universes. They're just separated from us so that we can't have signals. But there will be an overall mean density of this whole caboodle, and that would have to be less than the critical value for the universe to be infinite, rather than to be finite in size. Then there's a real problem. I've got to draw to a close, haven't I? Sorry? Nearly done. Okay. This is the biggest problem of all. The universe has to start off highly ordered at the beginning, and in order for it to give rise to galaxies, stars, and life. If I knock the glass off the table, you get a mess. You don't see glasses lifting up onto tables with their water jumping back into them and onto the table. That's the second law of thermodynamics. The universe has to start off highly, highly ordered. The problem is that it doesn't need to start off as highly ordered as it does in order to give life. You only need one solar system's worth of life in order to get one solar system's worth of order, as opposed to all the 100 billion galaxies worth of order in order to get life. And the upshot of that is that we are much more likely, on the basis of a multiverse, to be in a universe that's got one solar system in it compared with junk and chaos than a universe that is completely ordered and structured out as far as we can see. Monkey sitting on the typewriter gives to be or not to be. That is the question eventually. That, if you think of that as corresponding to a universe with life, well, we're not in that universe. We're in a universe that's much more like the complete works of Shakespeare, and that seems to me is a big problem. Okay, I'm not going to go into fake universes, but I'm going to say that the theistic explanation does provide an ultimate explanation why there should be life, because God has reasons to bring about life, intelligent life, and God freely chose to create this particular universe, intending that it produce intelligent creatures, and God will explain why the universe is as ordered and structured as it is, as opposed to just a solar system surrounded by junk. Here's my hero, Georges Lemaître, priest and cosmologist. There were two ways of arriving at the truth. I decided to follow them both. I'll end at that point. I mean, I do have a couple of questions if you wanted to look at those, but whatever you want to do in your groups, that's up to you. So I'll stop at that point. Okay.
Thank you, Rodney.
So looking just at the Big Bang Theory and nothing else, do you think that merely provides support for a deistic position, or can you derive a theistic position?
Yeah, that's a great. Yes.
You have to exercise some Christian love.
Yeah. Well, you're right.
Multiverse.
It does only get you so far in terms of an argument. So I think it points towards a supreme intellect, a super intellect that Hoyle was talking about, a great mind behind the universe. But it could be a deistic universe, a deistic God who sets it all up, and so on. I mean, that's not. So it gets you so far. It could be it's a starting point. I mean, I wouldn't want to stop with this if I'm doing apologetics. I mean, it's a starting point rather than a stopping point. So I believe in a theistic God who interacts with the universe. And of course, I think these people like Hawking are mistaken in that they, when they think that the only role for God is lighting the blue touch paper at the beginning. I think God upholds the universe moment by moment, and that's part of what we mean by the doctrine of creation, and interacts with it and so on, comes to live in it and so on. I think one wants to go further than the argument gets you.
Thank you. Let's move to the next group. I can see we do have convergence, as we put it in biology, of questions, but don't worry about that. The next group round.
Can we sort of send the second question back at you and ask a bit about how you think it would affect what Christians would believe if life on other planets was discovered? Would they also be prone to sin? Would they also need a saviour?
Yeah. Well, I think that's the big question, and I think there are two possible ways to go. I mean, and there's a difference of opinion even within Cambridge about this issue. So Brian Hebblethwaite, who's Anglican theologian, retired now, thinks that the idea of intelligent extraterrestrial life would disprove Christian doctrine, because he thinks that the incarnation has to be unique. Now, on the other hand, John Polkinghorne thinks that, well, if little green Martians sinned, they would need a saviour and so on, and God could become incarnate. And that I think, there's a very nice argument in the theologian E.L. Maskell back in the 50s. I mean, these issues have been thought about for centuries and centuries. Not that I'm just talking about the 50s now, but this whole debate goes back to Nicholas of Cusa in the 15th century and before that, and this idea that the fundamental question is about incarnation and so on goes back at least to a theologian called Varullion. Anyway, so Maskell and others think that the Chalcedonian definition, or Christological definition, is perfectly compatible with Christ being incarnate and saving other creatures on other planets. And I'm inclined to side with him on that. There's another issue which Polkinghorne raises. Well, even if they hadn't sinned, it would be rather strange that we were uniquely privileged in having God disclose himself, reveal himself in the person of Christ. You have to sin in order for that to be the case. So that's another issue that's raised. I mean, the evidence for extraterrestrials is, I think, actually very thin at the moment. The fact you've discovered these planets is interesting and very significant. It's very, very delicate, fine cosmological work that's going on, and subtle observations of tiny fluctuations in the light as the planet goes across the face of its sun and so on, of its star. But there are all sorts of arguments on the other side. Well, we've been looking for signals for the last 40 or 50 years from possible radio signals and not detected any. There's an argument that Enrico Fermi, as a distraction from working on the hydrogen bomb in 1951 over lunch one day, he started speculating, well, they're here. We're maybe 100 years or a couple of hundred years for having the capacity to go and go off to other stars, settle civilizations and so on, and you can do a rough calculation within 100,000 years we could colonize the galaxy. Well, that's small in terms of the age of the galaxy, so it's, why aren't they here as a consequence? So, I think the evidence, it needs a lot more work to actually verify that there are intelligent creatures out there. It might be bacteria, of course, who's worried? Because it's intelligent life. I mean, it would be very interesting, raise all sorts of interesting questions, but it's very open, I think.
Thank you. We'll move round to the next group. If your question has already been asked, then don't be afraid of passing. But,
if so many cosmologists have concluded that there must be a super intellect or a creator, why are so many of them still atheists, do you think?
Well, that's an interesting point. You see, I think that was a change in perspective from Hoyle, certainly. And someone like Paul Davis, I've talked about, is very kind of open to this kind of discussion. And he he certainly agrees that there's something that needs explaining, and he's uncomfortable with the multiverse. They try and find other sorts of explanation if they're still wanting to go the atheist route. So Paul Davies has this idea that the universe is a closed sort of causal loop, which you can sort of envisage in quantum theory. It's a very strange idea. Now, in this debate I was with him a few years ago, a colleague, a physicist colleague, working on quantum theory, said that it was pretty rude, actually. It's completely cracked, as an idea. So they do go. Martin Rees, who I got quoted, saying that, why there's a universe at all is a theological and philosophical question, not a scientific one. He goes for a multiverse because he's an atheist. He's open about it. He says it's only a hunch, it's purely speculative, but, I can avoid the need for God if I go that route. Leonard Susskind says, if he's right about his landscape of string theory, then it makes God redundant. Certainly to design he still thinks that with Rees that you haven't explained why there's a universe at all, but he thinks you can explain away the structure of this particular universe by invoking a multiverse. So there is a sort of atheistic motivation for going that multiverse route, not by everyone in the field, and of course theologians also, some of them, and Christian physicists also, that you've got multiverse proponents among them. So it's a mixed bag.
Thank you. And then across to the group at the back. And
we have a second question. As our first question was plagiarised by the group, we thought of another one. And it's really more on the view of the role of science and theology in the church today. Sorry, there, a bit closer. Is bearing in mind that it's difficult to prove the Christian God, yes, as it were, from this line of argument. Sure. Do you think, basically, put it this way, Polkinghorne and Barth will ever be dialogue partners in this one?
Well, I've written a book about Barth, and other theologians reacting to Barth. And on the one hand, I am a great admirer of Barth and his place in the Confessing Church in Germany in the 30s, the significant role he took, and how his theology was perhaps even the only theology that would work in that situation. But I'm very critical of him on the natural theology front, as indeed is Polkinghorne, and he's got, Barth's of course got his many supporters today, and he's got other people in the science-religion dialogue who are, who think there's a value to natural theology. So I think there is a value to natural theology for this kind of apologetic argument that gets you to some kind of supreme mind behind the universe. And as I was saying to the first question, I want to go further, and I think you need, Richard Swinburne is a very interesting philosopher who has come up with the idea of ramified natural theology, because I think you also need to argue and provide evidence and reasons for why we believe in the Christian God. So that means going into the particularities, and it needs going into the historical biblical criticism and so on. It needs going into the evidence for the life, death, and supremely for the resurrection of Christ. Now, I think with all the historical criticism, etc., we've had over the last couple of hundred years, our Christian beliefs and doctrine have held up very strongly to that. Actually, the fundamentals of what we believe. We might believe there are several sources for the Gospels, or whatever, but fundamentally what they're saying, I think, we can still argue very strongly for.
Thank you. One more question from this one, and then down the front.
Who's here?
not sure I'd like it, but I've got volunteered for it anyway. You've put forward some very convincing arguments for why the universe exists and there's life in it. But has cosmology given anything to what life is in itself? You know, it's a bunch of carbon and hydrogen and oxygen all stuck together, but how does that produce, you know, the life as we know it as well?
Well, that's a deep mystery, but I think I have to pass that one on to the biologists. We give them a planet, you know, all the materials that they need, and then you know, the biologists have to work it all out. Well, I think, and actually another book the very first book I wrote was about reductionism, and I'm very anti-reductionist. Of course, we're made of all those things, but we're more than the sum of all those parts. You know, I mean, Andrew was talking about complexity, and when systems get very, very complex, you start to get emergent features. So I think we have very significant features that emerge from the substrate of our physical makeup, of consciousness, self-awareness, rationality, free will, the ability to make choices, and so on, which maybe I depart slightly from Andrew, because I do think we're unique, and I think there's also a strong argument against certainly digital computers having the same capacities that we do. So, yeah.
Thank you. And one final question down the front here.
Yeah. I've got two possible questions. Okay. If the universe is expanding, does that mean it has a centre point? And if so, does that centre point have distinctive physical properties?
No. It's complicated though, because it goes back to Einstein's general relativity, in which you have curved space, and so. The universe can even be, if it's infinite, you can think, well, no, there's no centre. But if it's finite, there's still no centre in general relativity. And so the analogy is with a two-dimensional surface, the sphere of the Earth. If you think about the surface of the Earth, that surface has no centre. The North Pole isn't the centre. It's no different from any other point on the surface. Well, with general relativity, that kind of curved space idea, that curved surface idea, expands into a curved space idea, whereby there is no centre. From this here, we observe the expansion. If you move to any other galaxy in the universe, you would observe the same expansion.
Thank you. On that point, we'll close this session. Can we thank Rodney for his talk to us?